You're streaming, okay?
You're live?
Yeah.
Oh shit.
And then you'll have to learn jokes.
Hello everyone. This is quite a lot of unfamiliar faces here. That's a pretty pleasant surprise. I was expecting only my friends to show up, but I guess it's nice. So, a little bit about myself. My name is Indronil, and I'm primarily a self-taught classical pianist, and I'm learning bass and music production here at TSM. And the reason I'm here is that Gianluca sir, our Dean of Academics, he had asked me to initially talk about, what's a subset of this topic. Initially, in one of his theory lectures, in 1.1 theory, introduction to theory. But then we both eventually realized that 15 minutes is far too less to talk about a topic that can be so vast, and to explain anything properly would take probably far longer than that. Also, given the nature of this topic, given the nature of this topic, I think we would be missing out on a huge opportunity if I only explain to you the fundamental concepts. I do not take those concepts to the next level and address some things that, as far as I'm aware, a few very experienced musicians also do not know about. So that brings me here. And because this is basically a lecture on music theory, I think an appropriate first task could be to raise your hands if you do not like studying music theory, or at some point in time you've been disappointed by the fact that it exists. So raise your hands if you do not like studying music theory.
Not exactly. It's more like I didn't like it.
It's bad days.
Now I love it.
Okay, there's quite a few hands here. I was expecting more hands, but it's fine. So I'll tell you why I disagree with you guys. So, see, I've always been the kind of person who really likes to try to answer the question why whenever possible. In fact, and not just because it's extremely interesting sometimes, the answers. Also because it can be very, very practical. I think trying to answer the question, why does this sound good, is among the most important habits that you can develop as a musician. It literally defines who you are as an artist. You see, because when you really think about it, the kind of things that people write songs about and the kind of instruments and the arrangements, the production techniques that people use, they're not that many. It's often your unique perspective to that same idea, to that same melody, your own unique answers to that same question that you capitalize on when you write something original. So, to show you what I mean, I'm going to show you a little thought experiment sort of thing. So, let's see. So I just played two chords over here. I played a G dominant seventh and followed it with a C major, right? Now anyone with any experience studying music theory or trying to figure out chords to songs are familiar with this progression. They know it's a very popular progression. It's known as a 5-to-1 cadence or an authentic cadence. And the reason it's so popular is because it sounds great. Does anyone here know why it sounds great though? Anyone? Does anyone want to try?
Because the chord tones they're resolving to the tonic.
Which chord tone?
like the GBD,
Hmm.
B goes up to a C and like it resolves to the C chord.
That's actually correct, but that's only there's a good part of the reason, but that's not all. Does anyone know any other reasons apart from the B resolving to a C? I'll explain what he meant by that, by the way, but does anyone else want to try? Okay.
It's a sense of tension and resolution. Tension
Yes,
and resolution.
precisely, tension and resolution. This chord feels tense for some reason, we don't know yet. This feels resolved, it feels like home, right? So let's try to look at some of the reasons that I can come up with. So let's look at the notes that these two chords contain. In G7 we have a G, B, D and an F. In C major we have a C, E and a G, right? So as Jasveer just pointed out, a good reason is that B, the note B is known as a leading tone. You see, when I play the notes of a C major scale, right? What do you think this note wants to do?
Go up.
Right? That note really wants to go to the next one. The B wants to go to the C. And that adds to the anticipation that you get when you are expecting the next chord. So that is a good reason. So this note, the presence of this note adds to the tension that you feel when you play that G7 chord. Another reason is that it also contains the note F, which is called a subdominant note, if people care about it. Anyway, so this note over here, when I play this major scale in a slightly different way, if I play it like C, B, A, G, F, what do you think this wants to do? E, right? This F really wants to come down to the E. So even the presence of this note F, it adds to this anticipation of this next chord. As it turns out, it's not just these two things. It's not just these two notes. It's also the interval between them. When I play these two notes together, B and an F, this do not sound very, they're a tritone apart. The interval between a B and an F is a tritone, and you see, they do not, it feels like, you don't want to be here. You would much rather be here, right? Make sense? That's now I'm playing a perfect fifth. This is a very stable and nice interval as compared to a tritone, right? So these are already good enough reasons, but there's another very interesting reason that it's pretty weird. If I do not play any chords at all, even if I do not play any leading tones, any tritones, just the note G, it feels like it wants to come down to the G, C, doesn't it?
Yeah.
Right?
Yeah.
It's pretty weird if you think about it. I mean, I'm just playing a note, right? It just... So these are some of the reasons why. So let's see what we can come up with when we are working with these. So if you brainstorm a little, now let's see. You can see that this dominant chord over here contains a very special interval. It's called the tritone. Something very interesting about a tritone is that tritones are symmetrical, right? See, when you invert a perfect fifth, you get a perfect fourth. You get a different interval. You get a different interval when you invert most intervals, but not a tritone. When you invert a tritone, you get another tritone. So B to F is a tritone, F to B is another tritone. So if this tritone is such an important part of why this chord resolves into the next one, what that means is that, and given the fact that you can invert the tritone to get the same tritone, what that means is that there's another dominant chord somewhere out there that contains the exact same tritone interval. Does that make sense?
Yep.
And the exact same notes. And that happens to be a D flat dominant seventh. D flat is exactly a tritone away from G, obviously. So you'll notice that it has a D flat, F, A flat, and a C flat. However, a C flat is enharmonically equivalent to B, so we still have the same tritone interval. This is what it sounds like. So if what I'm saying was right, we can expect the D flat dominant seventh to functionally replace G seventh. I would expect it to have a very similar effect in a song when I'm using it. Let's see what that sounds like. So So I'm going to play a simple 1-4-5 progression first, and then I'll replace the 5 with a D flat. Sounds interesting, right?
Yeah.
You see what I did? Before I played a C followed by a F and then a G, and then later I replaced this G with a D flat dominant seventh, and it still sounded great, right?
Yeah.
And that's the thing. And so what we just did here is it turns out there's a name for it. It's called the Tritone Substitution. It's a very common thing that jazz musicians do. It's a nice way. It's an interesting way of coloring up your songs. When you have a normal progression, you replace random chords with this tritone substitute, and what you end up getting is something that sounds similar, something that sounds just as good as what you had before, but more interesting sometimes, right? It's nice to have options like that. So to see the important thing that we learn from this, it's not tritone substitution. It's also not this really cool progression that we just found. The important thing to learn is that it was the act of trying to answer why does a 5-to-1 sound good that led you to this new concept, right? Does that make sense?
Yeah.
If you had chose to be satisfied when I just say, okay, 5-to-1 sound great, and you just go on playing 5-to-1s in your songs, you would not have come up with this, right? It was because you asked that question. So that's why I found it, and that is what I'm trying to emphasize. You need to ask questions. You need to ask questions because the answers usually can lead you. You don't know what the answers can lead, what kind of knowledge it can unlock. Just imagine. Now we still have a lot of questions to go with if you think about it. What if I choose? Imagine the kind of knowledge you would unlock if you choose to ask questions like, why does the tritone sound unstable to begin with, and why does the fifth sound nice? Right? That's another question. I don't think most people know that. And now let's say we choose to, okay, so far we had ignored the fourth point, but let's say now we also think about it. It's actually very weird if you think about it. I mean, why does nature hate this note? Why does this G want to go to a C? Right? It doesn't make sense. It does not have any obvious answers. So this is these are some of the questions that I will answer through this lecture, and far more. And not just that, what I'm going to give you is a framework of knowledge that you can use to answer any kind of questions that you can come across in music theory or music in general. And yeah, that's it. I mean, and also to be able to do it on your own is perhaps the important part. You do not have to compromise your creativity by asking for answers from someone else, right? So with that, let's just jump right into the topic. And so before I start, just wanted to say that I'm trying to keep this as interactive as possible. So any kind of doubts, especially the stupid ones, are more than encouraged. And also I would feel far less anxious if if I feel that you guys are following me, you guys are interested in this. So that's that. So also I'm still recovering from dengue, so excuse my apparent lack of energy or enthusiasm. So let's same. Anyway, so the first part is about overtones. Is anyone here familiar with this concept?
Yeah.
What do you know what they are? You've already answered something else, Jairaj.
These are multiples of the fundamental frequency.
Yeah, but in some ways that you might expect the crowd to understand, if you may.
For example, there's
Yeah.
a guitar string vibrating,
Mm-hmm.
and if you plug it right in the middle,
Yeah.
the extreme ends of the string where it is attached will be like a half sine wave.
Right. I mean, you make sense. What you're saying is completely correct, but I think we can do a better job at trying to explain it to a person who has no idea about what these things are. Do you want to try?
Something which gives texture to the sound. To
Yes,
the note we are
you're
playing.
correct. It is something that gives texture to the sound, but how does it do it? So okay. So the first thing that you need to understand really to get anywhere in life basically is that music is essentially composed of vibrations, right? And vibrations of any kind has this one very important characteristic. It's called the frequency of vibration. The frequency tells you how many times in a given second does that thing in question vibrate. Does that thing go back and forth? So if I say that, I'm sorry, give me a second. So if I say that the frequency of the string is like, let's say 400 hertz, that means the string goes back and forth 400 times in a second. Make sense? Pretty straightforward. So now so basically every note has its own frequency of vibration. So when I play this note, it has its own frequency. When I play this, it has a different frequency. It has a higher frequency. And higher frequency means higher pitch. And that is how your brain decides this is how your brain distinguishes different pitches, because different pitches have different frequencies. You can tell this note is different from this because they have different frequencies.
Yeah.
This one has a higher frequency. But that is not all. When I play this note over here, sorry, give me a second, guys. Okay, so when I play this note over here, you know it's a piano. When I play the same note on an organ, or a distorted organ, you know it's something different happening here. I'm playing the same note, and now in whatever this thing is, you know. So the point is, and I can even sing the same note. You can tell when I'm singing the same note in different vowel. I can do a or a ah or a ooh. You can tell each of those apart, even though I'm singing the same frequency. So what that means is that there is something more to notes than just the frequency. Let's see what that is. So what I have right now over here is what's known as a frequency analyzer. What it shows you is that what frequencies exist in the spectrum. So you can see that when I play this note D over here, give me a second. Hello. So when I play this note D over here, you can see that there's more than one frequency. In fact, there's quite a few. Oh shit. I know. So you can see that. There seems to be a 300 hertz over here. There also seems to be a 600, something close to 600 hertz. Then there is a 900 hertz here. Then there's a 1200. This would be a 1500. This is an 1800. And you guys can see a pattern here, right?
Yeah.
It's pretty obvious. I'm not going to make it an open question and embarrass you. It's just multiples of the first frequency, right? So you can see that when I press this note, it has one main fundamental frequency, as it's called the fundamental frequency, and what the other ones are called overtones. The one at 300 is known as the fundamental frequency, the next one is known as the first overtone, then there's the second overtone, and so on. And all these frequencies are multiples of the fundamental frequency. Does that make sense? And when I say every note has its own frequency, I mean the fundamental frequency. When I say that this note has a frequency of 300 hertz, I'm talking about the fundamental frequency being 300 hertz. Okay? So let's see what happens when actually, one more observation that you could make over here. Oh no. Is that you see not all the frequencies have the same strength. You see the fundamental is pretty strong. The first overtone is slightly stronger than that, about as strong. The second overtone is less. Third is far lesser. Fourth, fifth is very less. Sixth is much higher in comparison. And you can see that the strength of the overtones generally reduces until it disappears, right?
Yeah.
So that's another interesting observation. Let's see what happens when I play the same thing on a organ. You can see now there's a lot there's again, you can see that there happen to be the same frequencies over there. You again see a 300, you again see a 600, 900, 1200, and so on. But now the overtones have different strengths. You can see now, you remember that the first overtone, the highest overtone was the first one. It was very loud before. Now it's not that loud. So the second overtone is loud. The third overtone is the loudest. And you can see a lot of very high overtones in this region that was missing in the piano. And again, it just disappears. And there's one extra nice overtone or whatever. So this is actually why your brain can tell these different tones apart. It is because every different tone has a different relative strengths of overtones, So a very interesting way to see this actually is on a guitar, which I will be showing you right now. So most guitarists are actually already familiar with this concept. They just know it by different names. They know it by the name harmonics. So you see, when I play a note over here, it again has a similar shape. Again, when I play a note on a guitar, you can see that you can see some overtones over there. You can see a fundamental at 300, 600. It's a different frequency, so the fundamental frequency is not different, but you can see that same pattern arising, right? But I think a better way to explain this would be on a with this diagram over here. You see, this is what the harmonics on a guitar look like. What this diagram means is that, so these are all the different ways. These are all the different ways in which the string can vibrate. So when the string vibrates in the fundamental frequency, it looks like this. There's maximum vibration at the center, and there's what's known as nodes at the ends. Nodes mean the points where there's zero vibration, there's zero motion. So there's nodes at the end of the strings, and there's maximum vibration in the center, and that is what the fundamental frequency looks like on a string. The first overtone looks like this. There's also a node over here in the middle of the string, and there's two bulges instead of one. The second overtone looks like this, the fourth like this, fifth like this, and so on. So when I pluck a guitar string, all of these are happening at the same time with different strengths, So again, so when I pluck the string slightly harder than other times, or if I hold the pick slightly tighter, or if I just strike it at a different angle, if I strike it at a different point in the string, if I change the pickups are very important, because if there's a pickup at this point, you can see that it will pick up certain frequencies very well. If there's a pickup at this point, it won't pick up this overtone at all. So when I change the pickup position, when I change the tone knob, by all these things, what I'm doing is I'm changing the relative strengths of these overtones. And when I do that, I'm changing the tone. That is how we express ourselves through a really nice instrument. So now a very cool way of seeing these overtones is when I put my finger lightly just over the 12th fret. When I do that, what I do is I make sure that 12th fret happens to be exactly at the middle of the string, by the way. So when I press my finger lightly over the 12th fret, what happens is I make sure there is a node at that point. And any overtone which does not have a node at that point disappears. It cannot ring. The fundamental frequency, for instance, cannot ring, because the fundamental frequency expects there to be maximum amplitude at the center. Make sense? Yeah. Right. So when I do this, you can see that you can only hear the first overtone. The second overtone disappears too, because it expects there to be a high amplitude over there. And you can see that you should only expect the alternate overtones over there, right? So that's what happens when I put it on the 12th fret. I could put it from my finger over the 7th fret as well. Now what that does, 7th fret happens to be exactly 1/3 of the string. And so now what happens is that now I make sure that the fundamental and the first overtone disappear, but the second overtone remains, because that anyway has a node at that point. So it can just play. and this is what it sounds like. So you can hear, and you should be able to see all this in an analyzer as well. So you see when I play this, you can see a lot of overtones. When I do this, alternate ones disappear. When I do this, we are left with less overtones now. We're only left with the second, fifth, eighth, and so on. Over the fifth fret, that's like 1/4 of the string length, even less overtones. Even lesser overtones. This is 1/5 the length of the string, so you're only hearing, yeah. Anyway, we can't hear the rest because these are the factors. I mean, because you saw, right, that the strengths of the overtones, they reduce as you go up higher in the series. So they usually tend to die out after about the fifth or sixth overtones. So anyway, a simple consequence of this overtone series is that are the concepts that are known as, no, before I tell you about that, one table I want you to see. This is important. This just tells you what the overtones, which note each of the overtones are. So if I say that F is 220 hertz, if I say F, the fundamental frequency is 220 hertz, and I call that note the unison, as it turns out, this is exactly that note, but I would expect a piano. Pianos are nicer, right? So you can see the fundamental is about 220. It's exactly 220, in fact. So the next overtone, twice the frequency, that is an octave above that note. 3F takes you a fifth above that note. 4F, another octave, another A. 5F is a new note because 5 is a prime number. It's a major third above A. This is C sharp. 6F. Now you see, whenever you multiply the frequency by 2, what you get is an octave above that previous frequency, right? And so if 3F is a perfect fifth above A and E, that means 6F, which is twice of E, it should also be another octave above E, right? So this is 6F. 7F is again another new interval. It's called the Harmonic Seventh. It is not something you can hear on this very well, but it's close to this one. 8F is an octave, 9F is a major second, and you can see this. So basically, when I play this note A over here, you can see what you're hearing is not just the note A. You're hearing the perfect fifth, you're also hearing the major third, and you're also hearing a bit of the harmonic seventh, which is close to the dominant seventh. The point being, notes typically in nature don't exist by themselves. Because of this overtone series, whenever I play this note A, you're not hearing just the note A, you're hearing an A major chord. You're hearing a bit of the dominant seventh as well, but A major chord is something that we are all very familiar with. So I think that answers the question why the note G wants to go down to C, even though there didn't seem to be any leading tones or tritones involved over there. When I played the note G, you're not just hearing G, you're hearing a G major chord. And then that brings us to the initial argument of why G major is also a C major, right? So because of this overtone series, that progression sounds nice too. And a simple consequence of this are the concepts called consonance and dissonance. Now, do you guys know what they mean? तुझे सब पता है और किसी को try करना है? Guys, anyone?
Consonance would be where something seems to harmonize, or in a sense just sound good with another.
Harmonize wouldn't be the right word because you can have dissonant harmony as well. Harmony, the word by itself does not require it to be consonant or dissonant, but when you said it should sound good, I think that's the word used. That is a better description of what consonance is. What this is a consonant interval. When I play these two notes together, they sound nice. They sound so does this, but if I play, they do not sound well together, right? It doesn't feel like it. Even this is weird. These are what's known as dissonant intervals. Why this is a consequence of the overtone series is that, you see, because you're so used to hearing frequencies in this particular pattern, because whenever you hear notes in nature, you always hear notes in this particular pattern, frequencies in this particular pattern, your brain is very used to, familiar with these. Your brain just really likes it when you hear notes in this ratio, like notes in a simple ratio like 1:2 or a 2:3 or a 1:3 or a 2:5, and when you hear notes when you hear two frequencies in these ratio, these are things because these are things you're already familiar with, your brain is programmed to feel good about it, feel like it's natural, right? And that is why, because some frequencies, the ratio between certain frequencies, certain pairs of frequencies are sometimes simple rational numbers. When I say rational, I just mean numbers like 2:3 and simple fractions like that. Sometimes they sound good. In fact, this ratio is exactly a 2:3. Perfect fifth is a 2:3. The ratio is 2:3, and a tritone is a 1:2 square root of 2. So it's not a nice ratio. That's why it sounds dissonant, right? So let's see what the next slide is. Is this okay? Consonance and dissonance. Okay, this thing. So this is an important table, I would say. This is something that tells you that which in the interval. This shows you the intervals that you're all familiar with. So you have the intervals here on the list, and this tells you what a simple ratio is. This is supposed to be a 9 over here. I don't know why it's not.
Mike stand.
Oh. It's a 16/9. So you can see that some ratios, like the perfect fifth and fourth, are like really nice. 3:2, 4:3 is a nice ratios. That's why they all sound very consonant. The red ones are like really dissonant. 16/15. You know what? So a 9/8 is like a major second. So let's just see what each of these sound like. You have the octave is a 2:1, so it sounds very consonant. Perfect fifth is a 3:2, also very consonant. The thirds and the sixths, they are like sort of consonant. They're like still pretty consonant. 5:4 is consonant. 6:5 also consonant. Because sixths are the inversions of third, they're also pretty consonant. Now the major second and the minor seventh, they are called mild dissonances because they are not nearly as consonant as this, for instance, right? So the mild dissonances and minor second and major second, they are terrible. They're not terrible, they're just very dissonant. So is the tritone. And the perfect fourth is a slightly controversial one. In fact, all of these are controversial, because this is not a very perfect description of what consonance is. It just happens that this is a very good factor. This is a very important factor, the fact that ratios need to be simple for things to sound consonant. So just want to say that these are not perfect descriptions, and you can always have, depending on the context, depending on what you played before, what you're going to play after, what other notes you have in the picture at the same time, these things could change. A perfect fourth can be easily made to sound dissonant, and sometimes you can even, if you're creative enough, you can have a dissonant octave as well. So I'm not that creative, but I guess someone would be, so there's that. I think that pretty much leads us to the end of this section. So does anyone have any doubts so far? No doubts at all?
What's 16 and 15?
Mm-hmm.
What are the numbers?
Sorry?
What are the numbers do? What are they?
Okay, this tells you that when I play a minor second interval, like a C to a D flat, for example, it means that I'm playing two different frequencies at roughly the ratio of 16:15. Like, of course, D flat being 16 and C being 15. Makes sense? Right? I'm sorry?
But why?
Why is it 16/15? It's just that is something I'll be answering in the next part of this lecture. But I think for now you just accept that it's 16. It's something close to 16/15. I'll tell you why it is that, or why we came up with that. You'll understand that pretty soon. So unless there are any more doubts, we can. Okay, go on.
You said that perfect fourth interval could be like made to sound dissonant. How is that possible? Like,
Okay, I'll
give an example.
show you something. So typically, one usage of a dissonant perfect fourth that I know of is that a perfect fourth is usually consonant when it's used as an inversion of the perfect fifth. What I mean is, if I play a C power chord, for instance, when I have a perfect fourth interval between the G and a C, right? In this context, it's very consonant, right? But if I use it as a perfect fourth, if I somehow now change if modulate it to G major, if I play this in context of a G major, now suddenly doesn't feel that consonant anymore, right? Because context, now this wants to go down here. Now this is more consonant. So perfect fourths typically, when by itself, are dissonant because it's surrounded by pretty consonant intervals, right? Another factor, you can also, in this case, the perfect fourth feels like it wants to go down to the major third, right? But according to this table, a major third is supposed to be less consonant than a perfect fourth. So perfect fourths should be theoretically more stable. But you can see that a major third feels more stable now, right? So that is an example of a perfect fourth can be dissonant. I hope that answers the question. Is there any more of those? Nothing? So let's move on. Do you guys think this is like interesting so far?
Yeah.
Right? Okay, because it's gonna get even more interesting now. So this part, okay, so let's just say we are all in like the 14th century or something now, okay? And yeah, let's not kill each other though, but okay, let's just say we are there. Now, let's just say you figure out some ways of creating sounds, and you've figured out things like, okay, when you have a string, you stretch it and you pluck it, it creates a particular frequency, creates a particular note. You figure out things like that, and let's say you also figured out things that I've told you, because there's a simple phenomena that you can observe around nature. So with all this information, if we just had to create a musical instrument, and when I say musical instrument, I don't mean like something percussive, I mean like something that produces notes, distinguishable notes. Of course, it doesn't have to be something as elaborate as this, but you know, what do you guys think would be a good first step? How would you approach this problem? Like, okay, so you figure out that strings produce notes, and you've also figured out some other ways of producing notes, but how do you proceed from there? So how do you go on? How do you improve that instrument of yours? Of course, it's a very long way from that simple string to this, and there's lots of different steps involved, but let's still try to brainstorm and figure out what some of those important steps are. So, does anyone want to try? And figure out what would be the next good step after having a string? Yes, Raj.
It should create different consonant frequencies. Like we should be able to.
That is a very interesting point. But I think most of us know that there's nothing inherently good about consonants and bad about dissonance. In fact, any good piece of music, any good melody requires a good balance of consonants and dissonance. It's like if there's just happy things happening in life, it's not a very interesting life, right? So anyway, moving on. So the point being, there's nothing good. The consonance is not good, dissonance is not bad, but he still said that we need to add consonant intervals. Now, why did you say that? Why do you think consonance is important?
Important as in we should be able to generate the different intervals on the instrument.
That is good.
There should be an octave, for example.
Okay, let me try to answer that question in an interesting way. I don't know if you... There's a simple mathematical fact that you can actually very easily prove that there happen to be far more irrational numbers than rational numbers. There's, in fact, more irrational numbers between 0 and 1 than there are rational numbers in the entirety of the number line. In fact, there are infinitely more irrational numbers between any finite space on the number line than there are rational numbers in the entirety of the number line. Why is that relevant in music? You guys understand what I mean by rational and irrational, right? It just means rational numbers are numbers like 3/2, like simple fractions. So how is that relevant in music? What that means is that consonance is rare, right? If you take any two random frequencies, the odds are very high that they're dissonant than consonant. So it is a very good step indeed to think that okay, we should add consonant intervals, because we can expect dissonance to show up regardless. So speaking of consonant intervals, okay, that is a good idea. So what intervals do we add then?
You start with the octave and
Start with the octave and then?
fifth.
Is your name Pythagoras, bro? Because that is exactly what he did. So that is literally what he did. So basically they just figured out ways of producing different frequencies from different strings. There are ways to change the frequency. If you have the same string, you can just add frets to it. When you add frets to it, you're changing the... Okay, I don't think I should need to talk about all that, but anyway. But there are ways. People figure out ways to produce different frequencies. And Pythagoras, this dude, he thought that... he came up with what's known as the Pythagorean tuning. This is the first tuning system device. And he did exactly what Aditya suggested. He added... So let's just forget that these notes are here, and we just have a circle, and the circle represents an octave. Okay. So the first thing he did was that define some note, right? And then he added a fifth above that note. Now he didn't call it the fifth, of course, but he just added a new frequency, which was 3/2 times the initial frequency. Let's just say, for the sake of simplicity, the first one was 1. The second one he added was 1.5 or 3/2. Now, after he did this, he thought, okay, let's now add a fifth above this new note. And when he does that, he get a ratio of 9/4, because that's 3/2 squared. And 9/4 is greater than 2. That means it's beyond an octave. So to bring it back to the same octave, you divide it by 2 again, so you get a 9/8. Make sense? So what you get now is a new note, a D. He defines this note by taking a fifth above G. And he takes a new note, defines a new note A by taking a fifth above D. He takes a fifth above A again to get a new note now. Now at this point, we actually have something special. You can see that the octave is about roughly uniformly divided. You see the 5 notes, they seem roughly equally spaced out. And there's something else that is special about these 5 notes. Does anyone see what that thing is?
Golden ratio?
No, nothing to do with that as far as I know.
All these are
No, try now.
all these are like kind of consonants except for the...
Yeah, they're a consonant, of course. We just added fifths,
Yeah.
stacked fifths on top of each other. They happen to be consonant. These are what? Exactly. These are notes of the pentatonic scale. Guitarists, come on, man. So this is like all you do or something. So anyway, these are notes of the C major pentatonic scale or A minor pentatonic scale, and so just something you know. This is how the pentatonic scale is actually built by stacking fifths above some starting note. Let's add more notes now. The latest note was E. Let's add a B and a sharp. Now we again have something special here. What is that?
Whole tone scale.
Nope. How is there a whole tone between B and C? Bro. Okay, so what is it this time? Come on, guys, this is not that difficult. Okay, I'm building up the circle of fifths, but look at the notes that we have so far. What is special about that?
It's a G major.
It's a G major scale. We have discovered the major scale, right? This is how the major scale is built. We take fifths and these are notes of the G major scale. So this is again something nice. This is how the major scale. This is actually the first version of the major scale. So now, let me just show you quickly what things sound like so far. You started with the C, and then you added a fifth above it. You got a G. I'm going to remove this thing. It's not interesting anymore. Right. We defined an exactly 3/2 ratio above it, and then we went from a G. We got a new interval now. We got a D. Sorry, do you have a doubt? Okay. So from a D we got an A. From A we get an E. We have these 5 notes so far. Sounds really great. And then we got a B and a F sharp as well, and we notes of the G major scale, the first major scale ever, and it just sounds good already, right? So it's like we are on the right track, right? Because we have a scale, and we can, with a major scale, we can already compose a lot of songs. We can compose a lot of music already with what we have. But let's move ahead. But because this doesn't feel very uniform, so let's try to see what else we can do. The latest note was, can I have some water, guys? I'm just really thirsty. So the next note would be C sharp, which we define as a perfect fifth above F sharp. You see the ratios have started getting slightly ridiculous now. What is a 2187? Anyway, the point being that all the fifths sound great because they're exactly a ratio of 3/2 apart. Then we get a new note, which is a G sharp. Then we get from a G sharp we get a D sharp. From a D sharp we get an A sharp, and from an A sharp we get an F. Now at this point the circle seems uniform again. The last such milestone was when we had 5 notes. Now at this point when we have 12, it again feels uniform. So it feels like a nice point to stop and give some names to these notes. And this is what happened. This is how the names of the notes came to existence. But there's another problem. You see, so far we have been defining all the new notes, right? Now, because if we are assuming this to be uniform, we would expect, if we are following the pattern, that we should rightly expect a C to be a perfect fifth above F. But you can see that the ratio between C and an F is not 3/2. It's 100. You see that number over there. And this is what it sounds like. Do you want a perfect fifth to sound like this? No, right? I mean, it sounds terrible. I'm playing the notes F and a C in this particular intonation, right? All the other fifths, they sound perfect. They're so great. It's like so consonant, about as consonant as a perfect fifth can be. But this fifth over here, the fifth from a F to a C, this is known as a wolf fifth because people somehow it sounded like a howling of a wolf or something, so they call it a wolf fifth. And that is because, and the reason it's dissonant is because the F does not want to go to that note over there, it wants to go to that note, right? And it doesn't feel, and adding that note would just be inconvenient because, like, why do you have 12 uniform notes, why do you want to add that note over there, right? So it's just stopped. And what's happening here, so what we have here, we have this error, like we have this, a comma in music theory is when a same note is defined in 2 different ways, and both those different definitions give you different results, slightly different frequencies, and the error in that frequency is known as a comma. In this case it's called a Pythagorean comma, which is roughly 23.46 cents. 23, like, it's just cents, what they mean is like basically a semitone is 100 cents, just remember that. A cent is a very small interval, it's just 1,1200th of the division of an octave, and 23 cents means like a little less than a quarter of a semitone. So that's called the Pythagorean comma. Of course, the higher the comma, the harder it is to make that scale sound nice. So, but this could be improved in an obvious way. You see, we only have sharps in this scale so far. If now we can do something slightly different. What we can do is, we know a perfect fifth is 3/2. we multiply by a number 3 by 2, you get a perfect fifth. Let's say we define a perfect fourth as the inversion of a fifth. When we do that, now inversion of a 3 by 2 is a 2 by 3. But a 2 by 3 gets you, 2 by 3 is a number smaller than 1. It gets you an octave below, right? To bring it up here, you need to multiply it by 2. So 2 by 3 times 2, which gives you a 4 by 3. So 4 by 3 we define as a new interval as a perfect fourth. And we define a G as 3 by 2 and we define an F as 4 by 3. You guys are following so far, right?
Yeah.
So now we just go about the circle of fifths, like you know, we get a G from as a fifth above D is a fifth above G, B flat is a fifth below F, and each time we define 2 new notes, we get a, right? And after this point, we have to choose, like, do we want to define it as a fifth above B or a fifth below D flat? And there are both. I mean, no one really cares because no one uses this, but you know, there's no right way to do this, but one way to do it would be just define it as the square root of 2, which means it's exactly at the center of the octave. It's neither, it's just something, a hybrid sort of thing. And in texts and references you can find all 3 variations of this tritone, but there are still some problems here. When we do this, the ratios are far less ridiculous, of course, but there's still other problems. Like, you can see that the interval from a B to C is far less than a B to a B flat. So you can see that these 2 notes are very close together, B and a C. I'm playing a B and a C together. If I play a B flat and a B, this is not a good example, wait. Am I using the right intonation? Should be that. Anyway, so where did that go? So what else can we see? Okay, let's compare A and B flat. A and B flat feel very close together. B flat and B are much further apart. You can see that, right? And you can see that from the diagram as well. So there's problems like that. This is an issue if you want to play chromatic things, like chromatic passages or anything. Also, by the way, this is exactly the definition. This is exactly how the notes are defined even today. Definition of an A is that it's a fifth above D, and the circle of fifths, the way we discovered it, is actually how the notes are defined even today in today's literature and music theory. So if you ever come across things where you do not literature where you do not understand why they are defining notes in the way they are, it's because they're defining it like this. So an obvious improvement to this would be, and also there are other problems, like the ratios are still pretty stupid. 256 over 243. No one in the history of humanity has heard the 256th overtone of any note, because that's literally outside the human hearing range probably. I'm pretty sure the 256th overtone of this does not exist in our hearing range. But so these are not ratios that you're ever expecting to hear. You don't want to hear ratios like this. So, and also sometimes maybe I just want a simpler ratio. So the next obvious improvement from this would be what's known as a pure intonation or just intonation. What that does is this replaces some of those ratios with simpler ones. Now you have most of them, some of them are the same as before. E now becomes a 5 over 4 because before it was an 81 over 64. That was the initial definition of an E. But now we are defining it as a new interval, a 5 over 4, which is very close. And now we have a new comma, which is known as a syntonic comma, because there's a discrepancy in how we're defining the same note. But there is still
the Pythagorean comma again?
Because we are in a Pythagorean comma was in Pythagorean tuning. Now we are in pure intonation, so syntonic comma. We just have a different name for it. So you see, the really cool thing about this is that things actually sound really good. So you see, the ratios in this are so good. It's like they're about as consonant as they can possibly be. This is literally the best version of the major chord you can ever hear. This is exactly a very nice ratio of 4:5:6. You're hearing 3 very nice frequencies together. good ear might feel that this is actually slightly off, which it is slightly off compared to what we actually are used to. But you see, intervals actually are very nice, right? So I could play some random thing in this, but never mind. So, but you get the point. Things sound extremely good in this. So, what is one very big flaw in this system, because of which we were forced to abandon this for something that, well, solve whatever the problem was. So, what is that one very big problem in this system?
Each key would have a different, so like if we want to have a C major, then that would have a different sort of tuning. D major would have a different.
Precisely. If I play the C major chord, it sounds like this. But the further we go up in the circle of fifths, the worse it gets sounding. And when I play the F sharp major chord, this is what it sounds like. Now you don't want this to be in your song, right? If you want a major chord, you're expecting something consonant to that point. But you don't. This is what the F sharp major scale sounds like. This is what a C. This is what a C sharp major sounds like, right? It's weird, right? Literally any chord with C is like pretty weird. This is the B major chord. You don't want this in a song, do you? You don't. But if you want to play things only in the scale of C major, everything sounds brilliant. So these are some of the problems, that non-uniform semitones make chromatic passages difficult. There's difficulty in key modulation, as this person pointed out. Also, there is still some ridiculous ratios that no one really cares about, right? 16/15 is not cool. I mean, when you play a minor second, you're not expecting to hear a 16/15 ratio, right? Maybe sometimes you just want a nice passing note between C and a D, something exactly in between, right? So what people did after that was come up with this really cool number. It's the 12th root of 2. This number means that it's a number that you have to multiply to itself 12 times to get the number 2. And with this number, you get this new system where everything is equally spaced apart, right? You have an octave and you have an exactly equal division of an octave. So you define this note as this number over here. When you take powers of this number, you keep getting all the new notes. And this is known as 12-tone equal temperament, or 12-tet. And this is what you all hear in your day-to-day lives. And now you can see that when I play things in 12-tet, I'm playing the same C major chord, but it suddenly feels more dissonant than you've ever felt it. But that's because you just heard this C major. So nice and consonant, right? Now this is the C major that you hear in your day-to-day lives. Now this feels dissonant now, suddenly, right? Did your chakras get aligned, bro?
No, tune it to the chakral frequencies.
What is that? Anyway.
Trust me, the chakral tunings really exist.
Okay, man, I'll look it up. So anyway, so this is C major in a 12th, and this sounds very weird suddenly. So good luck getting used to that in your day-to-day lives. Anyway, so this is a very important table actually. So this tells you that when you take this particular number and you take the powers of this number and you give names to these intervals, this column is telling you what the decimal approximation of this thing is, and this tells you a number that is close to these approximation. So Somen, I think was her name. Wait, does this answer your question? When you asked me 16/15 क्यों है? When you asked me 16/15 क्यों है? That is because we defined it as a 12th root of 2, and when we did that, we get a number that is close to 16/15, right? And you can see that when you take these numbers in this list, right, like 2⁻7/12 gives you something like 1.4983, which is very close to 1.5, right? 1.5 is 3 by 2, so you have something very close to a perfect fifth. In fact, it's not even 2 cents away from a perfect fifth. And you can see other things like 1.33 is like 4 by 3, this is close to 1.2 or 6 over 5. This is, you can see the other similarities here. But you see, some intervals are actually pretty terrible. The major third is 13 cents off from a 5 by 4, nice 5 by 4 interval, right? But okay, now, and it does feel very off now, but when we hear this in our day-to-day lives, we do not feel that off. In fact, we are quite used to it. What this tells you that, so everything that we just did, all these
Years.
all this centuries of experimentation, we started by adding consonant intervals, and we are like finding circles and all that. Everything was in vain, right? So we could have just divided an octave randomly into 12, and we were like, okay, we got some ratios that are close to nice rational numbers, and we're like, oh, that just works. And no one never feels that this is bad. They all like it. You all like it. So everything was just pointless and it's slightly disappointing. But if you think about it, if we were better mathematicians than musicians, then we would have actually come up with this sequence first. We would have we would have discovered that when we take this sequence over here, sequence of numbers, this power series, this happens to have really nice approximations to good simple rational numbers, right? So this, now because all that exercise that we just did about taking fifths and consonant intervals, it doesn't seem to matter anymore. It might make you question that what other numbers you could have divided the octave into, right? To also make sure that we get consonant intervals. Now that could be seen as a different way of coming up with a new system of tuning. Instead of adding consonant intervals, you can just think about how many steps you can divide an octave into. So that's an obvious next question, that how many steps you should split the octave into. And actually, in order to figure that out, I wrote a very simple Python script, which I'll just show you the results of. Like this. Anyway, what this code does is that it tries to. Okay, wait, I'll first show you what the output is, and then I'll show you. Anyway. Okay, so it spits out a list of pairs of numbers. So in this list, the numbers on the left tells you how many steps you can divide it into, and the number on the right next to it, it tells you how good the approximations are. Now it calculates that factor over there based on a number of things. On the basis of course, how well the approximations are, also in terms of how much better it is than its neighbors, and some things like that. So we end up with a list of these numbers. You can see that 12 has a very high score in this, but of course, depending on how I calculate this exact value, which actually has a lot of things going on here, you can have slightly different answers. 12 might not be the best if you calculate this slightly differently, but it still would be pretty good. So now that we have this list of numbers, on the left we have some numbers that when we divide the octave equally into, we can have nice consonant ratios, right? By the way, if anyone is interested in what I did exactly in this code, you can ask me later. I'll show you when I forgot. I think I did this a week ago. But anyway, so now I'm going to ask you a question that actually has no point at all, but it's just like, if you find it interesting, you'll find it interesting. I do. So you see this numbers over here. Do you see any pattern in this? Like, there's actually not any simple patterns here, but there is one very weird pattern just shows up, and I have no idea why. There's no one on the internet knows why this pattern exists. I have some answers, but not good enough. So does anyone see a pattern in these numbers? I'm going to give you... You can't see it? I'm really sorry. I'll just write down the first few for you.
Okay. Yeah, range is 5, 7.
There's a...
19, 22, 24.
Are you like blind or something? Like they can read it, dude.
Excuse me?
Anyway, There's a 12, 19, 22, 24.
29.
Yeah. Anyway, I mean, just look at, just like try, dude. Just you can come here if you want.
I got it.
So, did anyone get anywhere with this?
5.
बता ना.
3.
1, 2, 3 नहीं लिखा. मतलब, I guess you can assume 1, 2, 3 also exists here if you like. मतलब, वो तो they might have been filtered out based on algorithm, right? So, if there's 1, 2, 3, what do you do then?
Add the
Hmm?
I guess it's a Fibonacci series.
It's very good actually. Like, how did you come up with that, dude? Like, did I tell you this before?
I wasn't sure about 1, 1. So
3 नहीं है यहाँ पे शायद. But I think यहाँ ही start कर सकते हो sequence if you want to. क्या बोल रहे हो?
3,
Third, पता नहीं. I guess.
1 plus 2, 2 plus 3 plus.
But 3 plus 5 नहीं है sequence में.
2.
इसलिए, हाँ?
Yeah, so 2, 3, 7, like you added
Basically,
5.
yeah. So basically, when two numbers occur in the sequence, there's a very high probability that their sum also occurs in the sequence. You started with the 5, and you also remember that these two numbers were interesting because when we were looking at when we were adding nodes using particular tuning, so we had milestones at the points 5, 7, and 12.
Yeah.
If you remember, they happen to be parts of the sequence.
There's 12 and 7.
Hmm?
12 and 7 and 19.
I'm sorry.
12, 7, 19.
12, 7 and 19.
Yes, exactly. 12 and 7 gives you 19, which also has a very high score. 19 and 12 gives you 31. But you see, every number on this list can be expressed as sum of other numbers on the list as well. You know, except the first few. Sure. You can see a 53. This number has a very high score over here. That's actually a very interesting number. That is because you remember when I was in this slide, yeah. Yes, over here. So I had added this new note after F, which had made this circle non-uniform yet again, right? We don't like non-uniformity, so we could have chosen to add, define this as a new note and add a fifth above this one. That would have gotten us somewhere around here, and the fifth above that would have gotten us somewhere around here. And you can see, and the cycle starts getting more uniform again. But then, again, when you add the 53rd note into this octave, the cycle again becomes uniform. I wish I had the patience to animate that for you, but I really don't. So, but assume that, just believe me for now, that if you add 53 notes in this pattern, then you also get something that is very nice and uniform. You get something about equally spaced out like this, right? So, this is like really nice now. We can actually play chromatic solos now that we couldn't play before, because you know, when I play chromatic solos, when I play sometimes when I play the note D flat, I would expect something exactly between, a passing note between C and D. So this enables us to do that kind of stuff. It also means that the F sharp does not sound that great. Sorry, it does sound pretty great actually now. Not pretty great, but you know, good. Why is there no sound? Anyway, this is not nearly as bad as it was before. But then, you know, every major chord sounds exactly the same now because we have exactly the same ratios between every pair of notes, same number of semitones part. So you have this trade-off that C major not as this sounds dissonant now. I don't like this anymore. Anyway, so you have that trade-off that this is actually a dissonant chord, a little dissonant, but every chord is equally dissonant, at least, you know. So, is there any doubt so far, guys? बताना क्या हो गया? मस्त है क्या? बताओ, is anything you want to ask?
In the just intonation scale, you were playing just the C.
Yes.
In that scale, even the tritone sounds consonant or like.
No, not really. Let's just see though. Play कर देता हूँ ना. Actually, in the just intonation, the way I defined it was that 45 over 32. We could take some other pattern if you like though. See, it basically depends on the ratio, how you're defining it. I define it as a 45 over 32. This is how it's normally defined. Because a 45 over 32 is exactly a major seventh above G. So when you define the F sharp, you defined it such that you can now play a new scale, right? Before you could only play the C major scale. Now let's say you want to also play the G major scale and expect it to sound as similar as possible to the C major. You would define the new major seventh of G major as exactly what a major seventh sounds like over C, right? That's why you get the number 45 over 32, and this, as you might expect, is not consonant. A tritone is just
compared to the pure intonation, it's like more consonant.
I mean, that actually would have less to do with the ratio. I don't know. Actually, I don't know how consonant this is. So your question is if this is more consonant to then? I think whichever value is closer to a perfect fifth would be more consonant. But I think that would be an answer. But it's actually this question actually does not have any objective answers. Which interval is more consonant than which, right? We saw that before, that perfect fourth के बारे में भी तुम नहीं बोल सकते हो. So it's actually very hard. Both are about as dissonant. Is I think something you have to be satisfied with. So, but I want to show you something interesting though. Like if you now a minor seventh is usually considered dissonant, right? It was classified as a mild dissonance without a context. That is what it sounds like. But if I define a minor seventh as the ratio of 7 over 4, which if you remember was the seventh overtone, the 7F, the sixth overtone was harmonic seventh. You guys remember that, right? Yeah. That number was slightly lesser than what we have the minor 7 that we have today. So this is the root. Sorry, this is the root. This is what a harmonic 7 sounds like. This is exactly 7 times the frequency of the previous one. But I can see in a weird way this actually feels consonant, right? It has in minor 7th normally does not sound consonant, but this does, because this has a very nice ratio of 7 over 4. In fact, I figured out a way to make you listen to all the overtones until the 24th one. So if you have this as the 1, this is 2, 3, very consonant, 4, pretty consonant too, 5, 6, 7, 8, 9. This is if anyone with a slightly trained ear would feel this feels off, right, in a way, but it's actually not off. There's actually a much better ninth than the one when you're familiar with.
It's a bit flat, this tempo. So let's say
Let's see. I think this is flat. कितना सेंट लिख लेते हो? 11 cents flat. You're right. 10, 11.
This sounds
Interesting, right? It's like borderline consonant. This is probably the most consonant tritone you can ever have, right? This is 11 over 8 ratio, 11, and it is, and you can, I think, kind of see that it is consonant, it's more consonant than tritone normally sounds like, right? Anyway, this is a 12, 13, 14, 15, 16,
wow.
That's nice.
17, 18, 19, 20. Now it's just like they don't feel like consonant. They don't feel consonant anymore, of course, because these are all overtones that you don't normally hear. But anyway, this is 22. This is 23. Hey, this is not 23. This is 23. Oh my god. Anyway, and 24. This
will be okay.
it's the fifth. It's a G. So after about 7, things don't generally not. I think 11 maybe roughly. After that, things don't matter because you don't hear those overtones, because as you saw from that diagram in the beginning, that the strength of the overtones generally reduces as you go up higher. So anyway, that was a simple random thing that you can do. So we saw that 19 was a very good candidate, and you will find that a lot of microtonal music you'll find in random equal number of steps, random number of divisions of the octave. And most of those numbers will be actually on this list that I showed you before. And 1910 is actually among the more common kind of microtonal music. And you'll also find others that are not on the list, but they do not have very consonant intervals, and it would be an artistic choice to use it, but generally they don't sound very good. These numbers, they would sound good. So I could talk about a lot of different tunings, the theory, how it works in those, but I'm only going to discuss, I think, two that I find very interesting. One of them is 1910, of course, which I will talk about at the end, because I wrote a song in it and I wanted you guys to listen to it at the end. And the other one is known as a Bohlen-Pierce tuning. This is a particularly interesting one. The reason I'm talking about is that these two guys, they independently came up with this new, very weird system of defining their notes. So you remember earlier that something that we just took for granted is that we defined a circle and we defined it as an octave, right? We defined it as an octave because most cultures independently discovered this thing called octave equivalency, which is just like saying that when you have... Wait, I have to change the tuning first. Anyway, when you have this note and you play an octave, this feels like the same note, right? Why does it feel like the same note? Because all the frequencies that you hear when you play this octave are already in the overtone series of the first one, right? It doesn't feel like a new note really. It just feels like you're playing the same tone in a different patch, sort of, right? So that is the concept of octave equivalence. Every culture has discovered this concept on their own independently because this is something very natural. But if you really think about it, if that's the reason, all the overtones in all the frequencies shared by the G above this octave also happen to be in the overtone series of this particular note over here, right? Now when I play this new G over here, I'm not playing any new frequencies. I'm playing frequencies that already exist the moment I played this. You following, right? So you could have a weird different form of equivalence and also expect it to maybe sound good, right? It would not be as good as the octave equivalence because generally this overtone is much stronger than the fifth, but it still has the potential to sound good, right? And this is what these guys did. And what they did was took this new interval and they called it the tritave. I do not like this name at all, but they called it a tritave, this interval from C to the next G, and they thought, okay, fine, we want to define this interval as the point of repetition, okay? And see, before when we defined our normal Pythagorean tuning or whatever, we got a major chord in the beginning. A major chord is really nice. It has a simple ratio of the notes in a major chord have a simple ratio of 4:5:6. You can verify that easily if you look at the table or whatever. But they decided to have a different chord, different triad to define the notes in this scale. Now they thought of taking a chord of 3:5:7. Now, the reason it's interesting is that 7 is more than twice as large as 3. That means 7 is already beyond an octave. So the fact that you chose a different repetition point, longer repetition point, actually helps here because 3:7, the ratio extends beyond an octave, but it does not extend beyond the tritave. So that they defined as the main. I don't know if you're interested, but what they did was that they start with this note, and this is the tritave, which is 3 times the frequency. And they got like 3 notes over here, 3:5:7 in that ratio. Then they got the same ratio like this, like 3:5:7, and added new notes like that. And then when they did that, these 3 notes became in the ratio of 5:7:9. Now a new chord, and this chord you can define from here as well. Then you get a 7:9 somewhere, maybe here. Don't know exactly where they lie, but you get the point. They defined this new triad, and on the basis of that, they added notes in between the triad, and they did some more stuff like that, and added some more notes like that to make it feel slightly uniform. And then again, they did something that we were forced to do at the end of our Pythagorean tuning, that whole sequence of exercises. That was temper the scale, because you also want things to sound uniform, right? So they ended up with 13 notes total, and they tempered that scale equally. So what you have is an equal division of 13 equal divisions of the tritave, and it sounds like this. This is a perfect octave, and this I'm playing the note C and a G. I'm trying to, at least, but they sound like an octave, because no, they're not sounding like an octave. I'm really sorry. It sounds like it's a perfect fifth, bro. No, I'm playing the note C and then the next G over here.
But it sounds like major.
This is the major third and the
Major third, yeah.
Wait. I think I've had something wrong then.
unequal.
But it's still supposed to be. I don't know. Are you sure? Wait.
Yeah, it's definitely major third.
I think it's called the tritave because it's the third one. The octave we call it because it's the eighth note.
Yeah, no. That's just they messed up. They just chose to name it like that.
Can you play something on that?
Wait a second.
Oh shit.
This feels like a major third to you.
I
You say?
think C and C sharp will be the tritave.
C and C sharp.
And next octave का C sharp will be tritave. It's a major third.
It's a major
13 notes है ना? The 13th note will be.
Oh shit! You're right, dude. I'm sorry.
Yeah.
You're right. I'm really sorry.
What's that?
This is supposed to be I just had to go 13 steps of C, right? That gets me to a tritave. This is a perfect fifth, right? Yeah. So it actually sounds nice, right? So there's no octave in this, but there's a tritave, and there actually it sounds weird generally, and there's a lot of very weird theory in this. There's no major and minor chords. There's just in fact two kinds of chords. There's a wide triad, which is like a 3:5:7, and there's the narrow triad, which is the 5:7:9. So there's just two types of chords, and some people have somehow written pretty good music in this actually. I found this artist called Elaine Walker. I don't know the vocals at all, but she composed some good stuff. Wait, I'll make you listen to the studio version. I don't have it. I'll have to wait. I think I bookmarked it or something. There it is. Shit. Anyway, so it's just 4 minutes sounds, and let's just listen to it. I think it's like goes on like that, but it sounds nice, right? But and also weird at the same time. I'm sorry?
Sorry, I was just saying it's adventurous.
Yeah, it's pretty interesting. So that's all I have to say about this scale here. I didn't personally experiment with it. It's just you can. But okay, so the next thing I did experiment with was 19-tone equal temperament. That's the last thing I'm going to discuss. And I actually spent a few days just listening to my keyboard play 19-tet tuning. I made sure to not listen to any normal kind of music, so I so I start understanding this particular. I start feeling this particular tuning system, right? Just to that exactly. And also, I think it's also very interesting exercise for a different reason. You see, most of us, we do not get to have this experience where so sitting, when you're in front of a keyboard, let's say, and you have literally no idea what two notes sound like when you press them. You have no idea what to expect when you press any two pairs of notes. You just have a lot of sounds in front of you, and you're expected to be creative somehow. It's not a position that a lot of us have ever been, and even if you have never touched an instrument, just by virtue of hearing a lot of normal 12th music makes your ears slightly trained to that temperament. But 19th is very different, because all the intervals that you can play except the octave are things that you have never heard before, unless you've specifically looked for it. So it was a very interesting, I think it's a very interesting way of challenging your creativity in a way, to find the limits of your creativity. If you want to do that, you can try and experiment with this. So something I did, and turns out, okay, so we can actually use something that we did before. So okay, this looks scary, I know, but this is actually very, very obvious. This is what a circle of fifths looks like in 19th music. I hope most of you are familiar with what a circle of fifth normally is. It's just a way of modulating through different key centers. You see, because a C major and G major share a lot of notes, you can easily modulate between from a C major to a G major, and you can do that. But you can also say that it's because they are next to each other in the circle of fifths that you can modulate between them. This is how you can define the notes in the circle of fifths. So basically, if you look at these, this is the. I'm sorry for this font, by the way. I just really have a thing for cursive. I know it's difficult to read, but So anyway, you will see that when you divide this octave now into 19 parts, you have this new number, 2 raised to the power 1 by 19, the 19th root of 2, and you have to take powers of that if you want to get any ratios. And you can see that the 11th note over here is very close to the perfect fifth. It's close to 3 by 2. Okay, so it's about 7 cents away from that. So you have a perfect fifth in this temperament is 11 semitones apart. Not semitones, but 11 steps on this keyboard apart. And I think I should also make you listen to what it sounds like, right? This is what a perfect fifth is in 19th. It's off, right?
Just intonation.
It's not actually closer to just intonation तो exactly 3 by 2 है. 12 में 1.96 cents का रहा था, इसमें 7 cents का रहा है. This is actually a very important fact. The fact that 12th में your perfect fifth is absolutely perfect. Well, very close, yes. And how that helps is that because you defined the major scale using the perfect fifth, right? Using the cycle of the fifths, the major scale in 12th is actually the best version of a major scale you can have in equal temperaments. Does that make sense? Because you define the major scale using fifths. Because the major perfect fifth, and this is not that perfect really, because this is 7 cents off instead of 2. The major scale that you get here, sorry, not as great as you would normally have a major scale. But this is interesting because this makes you question what can you do in 19th better than you can do in a 12th, right? There have to be some things that you can do in this better than you can do it in that. And there are some interesting ways to go about it. Like, if you really look at this minor third over here, man. It's like 0.15 cents off. It's so good. And there's actually a different set of math that you can use to get appropriate equal temperament, appropriate number of divisions of an octave to best approximate a particular ratio. To approximate the perfect fifth, the best 12th happens to be a very good one. If you want to approximate the minor third, then the 19th happens to be the best one. And there's a way to get to that as well. If you're interested in that, you can ask me later. I'll explain that to you. So minor third is extremely good in this. So maybe you might think that maybe we can define a. Okay. Before we do that, let's just try to define the notes normally that we did it there. So we started with the C, and then we get a G, which was 11 steps ahead, right? Now the next note would be a D, and you would get a D by taking 11 steps from G. 11 steps from G would be 22 steps total. 19 steps takes you to octave, so 22 will be 3 steps from there. So that means a D would be 3 steps ahead of a C, right? In fact, you can do this for all the other. You can define all the notes like this, and you will find that the all the major seconds in the key in the major scale, they get converted to 3 steps. So if I go up 3 steps, it feels like a major second that you're used to, and when I go up 2 steps, so all the they feel like semitones. So what I'm trying to say is that before you had this sequence, right, whole step, tone, tone, semitone, tone, 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 semitone. So there was basically 2 2 1 2 2 2 1. Now instead of that, you have 3 3 2 3 3 3 2, right? And there's also, because of this, there's also an interesting way of naming the notes. What you have now is, whenever there was 2 steps before, between a C and a D, you had 1 extra note before. Now you have 2. So you define the first one as a C sharp, the next one as a D flat. They're not enharmonic equivalents anymore. And now, before between an E and F, you didn't have any notes.
Now you do.
Now you have 1 note. And that you can call E sharp or an F flat. Now those are enharmonic equivalents. Right? It's pretty cool, right? So
This answers a lot of questions about like why C sharp and D flat are not the same note.
precisely, this is what I was actually wanted to say, that it's the theory that you find out when you discover 19 tet. Actually try to explore 19 tet. It helps you in your normal tuning system as well. It forces you to ask those questions, like what is more fundamental? Is the circle of fifths more fundamental? Is the circle of fifths a consequence of the major scale, or is it the other way around? Most of you have heard it. Most of you have first been taught the major scale, and then we're like, okay, circle of fifths is a nice way to figure out what the key signatures are, right? But now it turns out the circle of fifths is actually more fundamental than the major scale, and you define the major scale using that.
Yeah.
Makes you question what is fundamental in music when you try to just go beyond these things. And that is, again, stressing the initial point I was trying to make. You try to answer why, and you get new information like this, right? So that's a pretty cool circle of fifths. And what else do we have? Oh, nice. This is really cool stuff. So, as I was discussing before, what are some things that you can do in 19 tet that you cannot do in 12 tet? So, before, we did not have a choice. What happens when you try to take a circle of major thirds, for instance, in a 12 tet scale? You just end up, what happens? You have a circle of fifths in a major scale, right? What happens if you just try to take any other circle, for instance? Like a circle of major thirds, for instance. When you take a C, and you take a major third above it, and take another major third above it, and then another one, you don't end up with all the notes. All you end up is an augmented chord, right? So you do not end up with all the notes. Let's try some other interval then. We'll try a circle of minor thirds, let's say. Then we just end up with a diminished 7th chord this time. We still do not end up with all the notes. The thing is that it could be said that maybe you can think of it this way, that you think of the circle of fifths in major scale because it's literally the only circle you can think of. All the other circles, because 12 is a highly composite number, is divisible by most numbers below it. The circle of fifths is literally the only option, right? You can divide it into a circle of whole tones. Even then, you would get half the scale. Circle of semitones would give you everything, but that defeats the point of alternate circles, right? So the circle of fifths and the fourths, which is the opposite, is the only circle you can think of in. But in this, imagine 19. 19 is a prime. You can divide it into any number of notes. In fact, augmented triads are not even symmetrical in this. There are 2 tritones here now. There's a sharp 4 and a flat 5. They're 2 different notes. Imagine how interesting that makes tritone substitution, right? So these are all these things because tritones are not symmetrical anymore. So you have 2 different tritone substitutions as to the dominant 5. So there's things like that. And one very cool thing that you can also do is that, so when you try to get a circle of minor thirds, circle of minor thirds would have been interesting because, as we saw, minor third is a very good approximation in this. But that ends up with a lot of notes very close to each other. I wish I could animate that again. So, but basically, what happens is that if you take 4 minor thirds, it gets you somewhere very close to the octave. So you have now a note which is not making the circle very uniform, and then you keep adding more notes, and the octave never becomes roughly equally split until you add the 19th note. So again, that does not give you a really cool scale because you don't want a lot of non-uniform jumps in your scale. The circle of minor third does not end up with a very good scale. But there's something very interesting that we can do in this 19. Where's the marker? Oh, there it is. So before, a perfect fifth was in 12th tab. A perfect fifth is 7 semitones apart because 2 raised to the 7 by 12 is close to that 3 by 2. So, and the next octave one is 19 steps away, and the next one is whatever. But the point is they're all odd numbers. They're all going to be odd numbers because 12 is even, right? But because this is 19, the first one is 11. The next one will be 19 plus 11, which is the 30. Now 30 is an even number. 30 is an even number. That means you can split it into 2. You can divide it into 2 15s. A 15 steps from the root takes you to what's known as a sub-minor seventh. It is, or augmented sixth, right? Yeah. So this augmented sixth interval, or the sub-minor seventh actually is a better way to do it. When you take this circle of, so what this means is that you can we can first get the pentatonic scale that you got before by just stacking fifths, right? But every fifth can be split into 2 sub-minor sevenths, right? Are you guys following?
Yes.
So when you do, so every fifth, as you saw, is because fifth is 30 steps apart, right? And 30 can be split into 2 15s. 15s are sub-minor sevenths. So every fifth can be split into 2 sub-minor sevenths.
Yeah.
Right? So that's exactly what we do. We just split each fifth into 2 sub-minor sevenths. A sub-minor seventh from C will give you this note over here.
Yeah.
And you add 4 new notes like this. And when you do this, and when you arrange these notes together in order, you get what's known as a enneatonic major scale. Now this scale is extremely interesting, I'll tell you. So see, the first thing, let's just try to figure out what it sounds like, right? It's already 19. Okay, so what the pattern? Anyway, so this is a C, D, E sharp. Oh no, man, I should have practiced this. Anyway, the thing is that you have 4 weird notes here. You have the E sharp and F double sharp, A sharp and B sharp, these things that you haven't heard before. But the rest of them are notes of the major pentatonic scale. So you can just choose to keep playing along the major pentatonic scale. Now you see, if I wanted to previously modulate from the key of A major to an E sharp major, I would have to do that along the circle of fifths, right? But now, and that would take a lot of steps actually. A to an E sharp is like, how many? Wait, let's just check out the fifth circle of fifths, right? So A to E sharp, A is here, and E sharp, where is E sharp? E sharp would be
G sharp के ऊपर.
here. So there is a lot of 1, 2, 3, 4. If I want to modulate from this key, from A major to E sharp major, there's 7 modulations along the circle of fifths if you want to do it. By the way, you can. What I'm saying is that you can see a circle of fifths as a way of modulating between keys because that means majors. In the major scales have similar set of notes, right? It would take you 7 modulations to get from A to an E sharp. But if you want to modulate, because we defined the enneatonic major scale based on sub-minor sevenths, if you want to modulate from A to an E sharp, A enneatonic major to an E sharp enneatonic major, it's only 3 steps away. An A to a B sharp key change would have been like really long traversal along the circle of fifths. Because A major and B sharp major have a lot of different notes, but A enneatonic major and B sharp enneatonic major only have 1 note that's different. Are you guys following?
Yeah.
Right? So something very interesting that you can do is that, let's say you're in A major, you want to get to B sharp major. So A major because A major already shares a lot of notes with the endiatonic major, you see the pentatonic notes are already there, the most important notes. You can transpose from A major to A endiatonic major, from A endiatonic major to B sharp endiatonic major, from B sharp endiatonic major to B sharp major. Does that make sense?
Yeah.
So really, it just opens up so many possibilities in terms of key modulation, right?
Yeah.
So these are some cool things that you can do, I think. And don't really know. I don't think I have more content. I'll just play to you guys the piece that I wrote. See, so it is going to sound weird. See, there's just no way around it because these are intervals that you're just not used to. But I still. Jaraj, did you mix this track? So basically what happens is that I created a shitty mix, but I sent this guy the stems and I haven't heard this track. Are you sure it's good? Should I play that?
Play your
Tika. So anyway, so this is the track. So just want to just keep in mind that just try your best to keep an open mind when you listen to this, because it's like one possible reason why it might sound weird to you. One possible reason for it sounding weird does not involve it being a shitty song, just because you're not used to these. I've got very mixed reviews about this particular song. Some people just really liked it, some people just found it really weird, so I just hope you're in the former group. It sounds like this. I hope it sounded, you were in the former group. Did you like it? Right, to be honest. Okay, so it felt weird, I think, right? It felt weird. It didn't feel weird.
It started very weird in the starting, but I got used to it and it felt nice. Yeah.
Right?
Exactly.
Okay, so yeah, it started feeling really nice to me because, as I said, I was in that zone for 3 to 4 days, right? But I was just listening to this, these started feeling normal to me, and then I ended up writing this, and then I sent it to my friends. They were like, some people found it weird, and I was hard to relate to those people at that point. But then, yeah, I eventually started understanding what they meant. I actually started feeling weird. I had lots of different phases, moods. Like sometimes I liked it, sometimes I didn't. I hope you liked it, and I think that's pretty much it. That's all for today. You know, like these are my like social media things. This is my username everywhere. Okay, this is like my name in reverse, and that is my name. If you forget that, it's that word in reverse. And I think that's it really. I mean, thank you for being a really cool audience, guys. I forgot to ask you guys, is there any doubts, anything that you want to talk about or discuss? Patana?
With the, I don't remember the name, so it had a PS in the...
Boolean PS,
Yeah,
Boolean PS.
in that one, there was a C and a G above the, it was like a 13, yeah?
The 13 steps took you from
Yeah,
a G, C
30
to
steps
a
from
G,
that. So
yeah.
how did they, was that like an arbitrary choice that they made? Or
No. Actually, when they were, as I said, they were trying to define those triads, right? They defined a few more triads. I'm sorry, I don't have a complete explanation for this, but there's a very good video about this by 12Tone, a channel called 12Tone on YouTube. It has this video on exactly what I told about the scale and more. This describes it better.
Okay.
And so they usually use those triads that I told you, the wide one, the 3:5:7, and then the 5:7:9 one, and they added notes. They got a few notes like that. They filled in with a few more notes to make that for more uniform.
Also, so they didn't decide on the 13 and then fill it in?
No. They were adding notes based on the triad, and while they did, they somehow ended up with 13 seemingly uniform. Then they tempered that to 13 equal divisions.
Okay.
Make sense?
Yeah.
So anything else, guys? Hello.
Taking a few steps back,
Mhm.
the idea of consonance and dissonance and how the frequencies of something relate to something else. So the ratios that were being described by each intonation system, do they have anything to do with the constructive and destructive interference of each frequency?
Constructive and destructive interference? No, not really. Constructive interference is a topic that really starts to matter when there are two different frequencies. The same frequency, which are a phase apart. So interference is something that happens when you have this frequency, and you take the same frequency, but you start it from here. So now this peak over here cancels out this thing, this one cancels out this thing, so you have what's a destructive interference. If you had them in the same phase, they would add up. That is interference. So interference is something a term that happens when there is same frequency. When there are different frequencies, it doesn't have a lot to do with that.
Say you have like a beat frequency, right?
Yeah.
So it's like say you have somewhere 400 hertz, 401 hertz.
Yeah. Then you have a beat. Yes.
Yeah. So I was just wondering, how does that play into the?
That, as far as I know, does not have anything to do with consonance. That is a separate phenomenon of its own. You know, when you have
like even in certain chords, especially chords which have notes very close together, there is that like texture of like
Exactly.
notes coming in and going out, right? So that's what
I think, so you can think of it this way, right? So you have the ratio, for example, 100, you have, let's say, 100 hertz and a 120 hertz. So far I only talked about ratios. I did not talk about where those lie in the spectrum. If you have ratios of 100 to 120, they would probably not sound very consonant, because 100 and 120, because should I switch this off? This is 5/6, of course, but it's like playing a minor third in a very low spectrum, very low end of the thing. The reason why it does not sound that consonant is because the beat, the phenomena that you were just talking about, that phenomena starts acting independently. When you take the ratio, when you take the frequencies 50s to 60, you have the same interval, but in the octave previous to it, right? So now the difference between the frequencies is 10 hertz. Before it was 20 hertz, so there were less intense beating.
So
this as the factor starts acting independently.
Okay.
Right? So that's why the same interval, when you play it on a low register, it sounds dissonant. Because this beating factor, that's a very good point that you brought up. Thank you for that. So this thing, right, of this phenomenon of beating, you guys are aware of what beats are, right? Does anyone have a doubt what that is? No. So that phenomenon acts independently, as far as I know. If anyone has a better answer to that, this would be a good time. So I hope that answers the question.
You'll be outside for one more question.
You can ask me right now. If you
I
want.
want to show you something. Right?
Okay, sure. Anything else? Everything is fine?
Yeah.
So you guys like go or something?